Hi boys and girls, this is lecture 7.8, the topic Volume, the Disk Method, Part 1. If a region in the plane is revolved about a line, the resulting solid is a solid of revolution, and the line is called the axis of revolution. The simplest such solid is a right circular cylinder or disk, which is formed by revolving a rectangle about an axis adjacent to one side of the rectangle. We have this depicted here, a rectangle adjacent to an axis of revolution. If we revolve that rectangle around the axis of revolution, a solid is generated, a solid of revolution, which in this case is a right circular cylinder or disk. The volume of the disk is the area of the disk, and since the face of our disk is a circle, the area will be pi r squared, where the radius is the distance from the axis of revolution to the edge of the disk times the width of the disk, pi r squared w. As seen previously, we are able to take representative elements using a known pre-calculus formula, in this case the volume of a right circular cylinder, and sum them up using integration. This process results in an integral which calculates the volume of a solid of revolution. Our known pre-calculus formula, pi r squared w, the volume of a right circular cylinder, it becomes our representative element in the integrand, pi times the function value squared dx, representing a width on the x-axis, and this becomes our new integration formula. Pi on the outside of the integral, we're integrating from a to b, some distance on the x-axis, r of x, our function squared, this is our radius squared, times dx, which is the width of the disk that is generated. The disk method. To find the volume of a solid of revolution with the disk method, use one of the following. If your representative element is being revolved around a horizontal axis of revolution, use this integral. Pi on the outside, your endpoints of integration a to b, and interval on the x-axis, r of x, quantity squared, this is your radius, a function curve in terms of x, and then dx, which represents the width of the disk. If you're revolving your representative element around a vertical axis, use this integral. Pi on the outside, endpoints of integration c to d, an interval on the y-axis or the vertical axis of revolution, r of y quantity squared, this is your radius squared, a function in terms of y, and then dy, which represents the width of the disk. Find the volume of the solid formed by revolving the region bounded by the graph of f of x equals the square root of sine x and the x-axis 0 less than or equal to x less than or equal to pi about the x-axis. This is the region being described. Here's the function curve, the x-axis 0 to pi. This is our representative element, which will be revolved around the x-axis, a horizontal axis. It's going to form a representative disk as it's revolved. Now remember, the disk has a width, dx, and the idea would be that it's a virtual width. The radius of the disk is the distance from the x-axis to the function curve. So f of x is our radius, and the dx is the width of each disk. Now the idea would be that if we could draw an infinite number of these disks and add up all of the volumes, we would calculate this total volume of the shape depicted here. The integral will do this. So let's set up this integral. Remember, this integral is based on the formula, which is the volume of a right circular cylinder, pi r squared h, or times the width. And so when we set up our integral, we'll have pi on the outside, then the endpoints of integration, in this case 0 to pi. Our radius is our function curve, which is the square root of sine x squared. This is r squared, and then of course the width is dx. This integral will calculate the volume of this shape. So let's find this integral. First, I'm going to simplify the integrand a little bit. Pi on the outside, 0 to pi. This is actually the square root of sine x squared, which gives us sine x dx. The integral of sine is negative cosine, so we're going to have pi times negative cosine x from 0 to pi. This means we'll have pi times negative cosine of pi minus a negative cosine of 0. Cosine of pi is -1, so this will be -1, which is 1, plus cosine of 0 is 1. This gives us a volume of 2 pi cubic units for this solid of revolution. In this example, we're going to find the volume of a solid of revolution by revolving a plane region around a horizontal axis that is not the x-axis. Find the volume of the solid formed by revolving the region bounded by the graph of f of x equals 2 minus x squared and g of x equals 1 about the line y equals 1. Here is the region under discussion. We have 2 minus x squared and the line y equals 1, and our axis of revolution will be the horizontal line y equals 1. This is our representative region, and revolving it will form a representative disk. The width of the disk will be dx since we are revolving around a horizontal axis, but the radius is going to be the difference between the two function curves. Realize that the value on this function curve is measured from the x-axis. So in order to get this radius, we need to subtract from the upper curve the bottom curve, which will give us the radius at all points along this interval. Therefore, the radius function in our integrand will be the difference between these two functions, f of x minus g of x. That will be 2 minus x squared minus 1, resulting in a simplified radius function, negative x squared plus 1. In setting up our integral, we'll have pi from -1 to 1, the radius function, negative x squared plus 1, quantity squared dx. We are going to have to FOIL that binomial expression, so we're going to have pi from -1 to 1 of x to the 4th minus 2x squared plus 1 dx, and now we're ready to integrate. Pi times 1/5 x to the 5th power minus 2/3 x cubed plus x, integrating from -1 to 1. First, we'll plug in the upper endpoint of integration, and that will give us 1/5 minus 2/3 plus 1. And now plug in the lower endpoint of integration. We're going to have 1/5 times -1 to the 5th power minus 2/3 times -1 cubed minus 1. Continuing to simplify, we'll have 1/5 minus 2/3 plus 1 minus -1/5 plus 2/3 minus 1. This results in 2/5 minus 4/3 plus 2, giving us a volume of 16/15 pi cubic units, which is the volume of this solid of revolution. The washer method. The disk method can be extended to cover solids of revolution with holes by replacing the representative disk with a representative washer. This means that our representative element, the rectangle, is not adjacent to the axis of revolution. Therefore, when revolved around the axis, there will be a hole in the middle, giving us a washer instead of a disk. If lowercase r and uppercase r are the inner and outer radii of the washer, and w is the width of the washer, the volume of the washer is given by pi times uppercase r squared minus lowercase r squared times w. This represents the outer radius squared and the inner radius squared. The resulting region is bounded by an outer radius, uppercase r of x, and an inner radius, lowercase r of x. When revolved about its axis of revolution, the resulting volume is given by this integral, pi from the interval a to b, and then outer radius squared minus inner radius squared dx. Note that the integral involving the inner radius represents the volume of the hole, and it will be subtracted from the integral involving the outer radius. Find the volume of the solid formed by revolving the region bounded by the graphs of y equals the square root of x and y equals x squared about the x-axis. Here is the region being described. The upper curve is the square root of x. The lower curve is x squared. You can see that as this region is revolved around the x-axis, there will be an opening in the resulting solid. So here's our plan. We'll take the outer radius and calculate the volume of a solid of revolution. We'll take the inner radius and calculate the volume of a solid of revolution. Then we'll take that inner volume and subtract it from the outer volume, giving us the volume of the resulting solid with the opening in the middle. So here's how this works. The volume of the solid calculated using the outer radius will be pi uppercase R squared times the width of the representative disk. The volume of the solid calculated using the inner radius will be pi lowercase r squared times the width of the disk. Subtracting those two will give the volume of the resulting solid. Since the representative width is dx in the integrand, let's factor out pi and w, leaving uppercase r squared minus lowercase r squared. Now let's transfer this to the integral. We'll have pi, the integral, then uppercase r squared minus lowercase r squared dx. Now remember, these radii are the function curves. So in this case, we'll have pi. Outer radius will be the square root of x squared minus inner radius, which is x squared, squared, and of course, dx. Now all we need are the endpoints of integration. Let's get some practice finding those analytically. We'll set the two functions equal to each other to find points of intersection. The square root of x equals x squared. Now squaring both sides, I have x is equal to x to the fourth. When I subtract the x over to the right side, I have x to the fourth minus x. Let's factor out an x, and that leaves x cubed minus 1. When we factor x cubed minus 1, we have x minus 1, and then x squared plus x plus 1, since that's difference of cubes. This yields two factors which will tell us x values where these two functions intersect, at x equals 0 and at x equals 1. So our endpoints of integration, 0 to 1. Now let's integrate. First, I'll simplify the integrand a bit. Pi, and then we have 0 to 1. The square root of x squared is x, and x squared squared is x to the fourth. Dx. The integral will be pi times 1/2 x squared minus 1/5 x to the fifth power, integrated from 0 to 1. This will give me pi times 1/2 minus 1/5, and then inserting the lower endpoint of integration only yields 0 values. This means my volume is 3/10 pi cubic units. That's it for today's lecture. It's always nice to have a few new dance moves. Just don't get carried away. God bless you, boys and girls.